Hello, and welcome back to College Algebra, MAT 150. In this lecture, we're going to be looking at the radioactive decay model. So this model is given by A of t equals A naught e to the negative RT power. And it should look pretty familiar. In fact, it looks just like the standard exponential growth model, with one exception, the negative out in front. So we call R the relative decay rate, T is the elapsed time, AT is the amount after time. So as it turns out, if you have a material that's radioactive, it is going to, the amount in the of that substance will decay over time and will become less and less. And it turns out there's this thing called a half-life, because it won't grow, it's decaying. The time that it takes for the amount to become half of the original amount is given by this formula, T subscript 1/2. So this 1/2 right here has no computational value. It's just acknowledging this is the half-life time, because the half-life is a time. And it equals ln of 2 divided by R, where R is the relative decay rate. All right. So let's do an example. So if we have a thing called polonium-210, apparently it has a half-life of 140 days. So suppose a sample of this has a mass of 300 milligrams. Well, we want to find a function that models the mass of the remaining substance after t days. All right. Well, let's do this. So we want to find the model. So again, we're going to use our new model. It's the same as the exponential except for the negative and the exponent. So A of t equals A naught e to the negative RT. Do we have an initial amount? We do. That's the 300 grams. Or milligrams, excuse me. And the problem is that we have R. Okay, we don't know what R is. It doesn't tell us what that is. It just tells us a half-life. But this is something important to know. And this is the only other sort of type of flavor of problem that we could have is when we're dealing with the half-life, maybe if it's asking us to compute or use it. But in this case, if we have a half-life, which is 140 days, well, time, in this case, it takes 140 days, so 140 days could go in place of this, and we could solve for R. So that's what we're going to have to do. We have A naught, but that's not enough, and we need the R. So the half-life is 140 of this 140 days in particular, and it equals to ln of 2 over R. So the important thing to know is that when from this half-life formula, if you have the half-life, you have the relative decay rate. If you have the relative decay rate, you have the or radioactive decay rate, you have the half-life, okay? So from that, we can just solve. So I can multiply, again, we have a fraction, so multiply both sides by R. So 140 on the left side, we have R times 140 equals 140R. And then ln, we multiply this side by R, the R's cancel. So to solve, you can then divide by 140. So R is equal to ln of 2 divided by 140. So it turns out the half-life and the R can just more or less swap positions if you're trying to solve for one or the other. All right, so we need to compute what this is. We could just throw this into R, but it will make computations a little bit of a nightmare. So let's go back to our handy-dandy calculator. So ln of 2 divided by 140. So let me go back through and show you the full computation. So you can see ln of 2, and then we can, because we closed the parentheses, we can go ahead and we can actually do this all in one fell swoop, divided by 140. Or we could do ln of 2, hit enter, and then hit divide. It will give us the same thing. 0.00495. So we're going to go to, how about we go to 4 decimals, so 0.00, and then we need to go to 49, but the 5 rounds up, so we're actually going to go to 50. So we just need to put in 0.00 5 into our r, since it rounds up. So that gives us a of t, scooch this over so we can see it, equals 300 e to the negative 0.005 t. This is our r. All right. Now that we have the formula, we can do some computations. So let's first rewrite our formula down here. So it says find the mass remaining after 1 year. So let's just rewrite this so everything's not off the screen there. All right, so let's remind ourselves. So this is our formula. And the way we computed our R was from this, dividing by 140. 140 what? 140 days, okay? So the question is asked, find the mass remaining after 1 year. So what would that be? Well, as it turns out, we're not going to plug in 1 for t because this R, this relative decay rate, is based on days. So our time is in days. So how many days in a year? And technically it's approximately, but about 365. It's really about 365.24, but we're not going to get that technical here. Just an interesting little factoid. So we plug in 365 for t, because the R is based on days, so we can't just plug in 1 for years, equals 300 times e to the negative 0.005, and then times 365. And now we're going to go to our calculator. And this time we're actually going to see if we can do it all in one fell swoop. So it's 300, let's see if we can do this. 300, then multiply, we need to find e in our calculator. Here's e, so we notice it's in blue, so we have to hit second e. Okay, and then what we're going to do is we're going to plug in, so it's already in parentheses, so it starts a parentheses for us, negative for the record. The negative for these calculators are down here. This means minus. Okay, so this negative is what you use for saying negative. This is what you use for minus, so as an operation. Just for clarity here. A negative 0.005 times 365, and that was all in the parentheses. We just hit enter, and then we get this answer, 48.365, which rounds up to 48.37. So it's about 48.37 milligrams of polonium-210. Again, milligrams of what? Milligrams of polonium-210. All right. So we did one of those flavors. So this was the plug-in type of problem. We could also have the other type of problem where it asks how long will it take for the sample to decay to a mass of 200 milligrams. So our formula is A of t equals, remind ourselves, 300 e to the negative 0.005 t. And we're trying to find out how long will it take to get to a certain amount. So 200 equals 300 e to the negative 0.005 t. So this is the other flavor where we set the whole thing equal. Now we need to solve, so that means we need to isolate the exponential. That means we need to get rid of what's in front, so it means we need to divide. So when we do this, we're left with 2/3. No need to put that into a decimal yet. E to the negative 0.005 t. We need to solve for t, so we need to get it out of the exponential. That means we need to find an equivalent equation. So the equivalent equation for an exponential will be a logarithm with the same base, so base of e, which means ln. The output of a logarithm is, or of an exponential, is the input of a logarithm, and the input for an exponential is the output. So the exponent becomes the output of the logarithm. Negative 0.005t is what it's equal to. Then to solve for t, we just divide by negative 0.005. And then we have t, so this is a precise answer at this point, ln of 2/3. Exact, I say precise, let me rephrase that, it's exact. I'm going to put the negative out in front, 0.005. But this is approximately, and now we're going to have to go to our calculator. So 2 divided by 3. And then we're going to ln, and this is an interesting thing. So here, the answer didn't immediately come up. So there's a little trick. You can hit second, and there's a little thing down here in blue that says ant, so it's blue ant. So the blue thing means you need to hit second first. And when we do that, it puts in the answer for us. So second, and then that little, basically the same button that we pressed for the negative becomes that. And we're going to do ln of that. And now we're going to divide by the negative 0.005. Oops. Divided by negative 0.005 in parentheses, so make sure that I get the negative in there. And again, this negative is different from this minus sign. It's this negative, not that one. And we're going to hit enter. And we get t is about 81. We're going to say we're going to round to 2 decimals, so about 81.09. And what are the units of time in this case? They are days. So it's going to take about 81.09 days for the our initial amount of 300 milligrams of polonium-210 to decay to 200 milligrams of polonium-210. All right. So this is one example of radioactive decay. So we had to use half-life to get the R as the basic idea here. So it turns out there's another way. Again, as I was mentioning in previous videos, sometimes the calculation to actually get the model can be a little bit more difficult. So and this is a great example of something like that. What about if we had this example? Suppose that an element has a starting mass of 400 grams, and then 5 days later it has a mass of 300 grams. Well, first off, that thing is so radioactive, you need to get way away from that thing, okay? But jokes aside, we need to use, so to actually talk about this mathematically, we want to find the model. Well, the basic model is A of t equals A naught e to the negative RT. So we have that to start with. What is A naught? A naught is, so starting mass of 400 grams. Oops, started to put the wrong number there. That's why we read the problem several times. So 400 milligrams. And then does it talk about the relative decay rate? It does not. So what we're going to have to do is we're going to have to solve. So A of t equals 400 e to the negative something. We're going to have to find out what that is, okay? So how do we find that out? Well, as it turns out, the fact that we have this, so right now we have this model, 400 e to the negative RT. But because of that, we have 1 variable, 2 variables, and 3 variables, the relative decay rate, the time, and the amount. Well, as it turns out, there is a bit of information that we have. 5 days later, it has a mass of 300 grams. So we could plug in at 5 days later, we know we have an amount, and then we can use that to solve for R. So 300 grams equals 400 grams equal times e to the negative R, 5 days, negative R times 5, which is 5 days later. And now we're going to solve for our r. So we isolate the exponential, which means we divide by 400. And then 300 divided by 400, we can just cancel out the zeros, 2 zeros here, 2 zeros there. So 3/4 equals e to the negative r times 5 is negative 5r. We can just simplify that. We have a logarithm with a base of e. So ln, or we have an exponential with a base of e. So we're going to have an equivalent equation to solve for the exponential an equivalent equation with a logarithm with a base of e. Output of the exponential becomes the input. The input of the exponential becomes the output. And then we continue to solve. So divide by negative 5. And we have r is equal to ln of 3/4 divided by negative 5. And, or we can put the negative out in front. Probably should have done that. But this is approximately what? Well, again, we're going to have to use our calculator. So 3 divided by 4, that's 0.75. And then we're plugging this into ln. So again, we can do second. So we have to do ln. So ln's there. So ln. Now we need to bring back the 0.75. Again, we could just type it in because it's easy, but if you don't remember, again, hit second, and then hit this, and when we do this, I'm going to bring it back up so you can see, A and S will pop up, again representing the previous answer. Hit enter, then divide by negative 5. And we could put parentheses there if we wanted to. But that gives us about 0.057. We want to round to 4 decimal places since it's 0.0575. That's the fourth. The previous one is 3, so we're going to round down. So we're just going to have 0.0575 for our r, for our calculation. So take this for our r, and plug it into our formula, and what we're given is this. So our model is A of t equals, let's make a little bit more room here. Sorry about that. A of t equals the initial mass of 400 grams, grams, excuse me, e to the negative 0.0575 t. And this is our model. All right. So far we've, again, still followed the same formula of everything we've been doing. But now we're going to run into the only other type of problem that you could really encounter in this section, is where it specifically asks you to find the half-life. So if it asks you to find the half-life, you're going to use the formula, t of 1/2 equals ln of 2 over r. And again, I want to express that this formula is pretty straightforward, but it says basically it says if you have the half-life in time, then you have the relative decay rate. And if you have the relative decay rate, then you have the time. Since we literally just got done solving for the relative decay rate, we're going to plug this in straight away, and we're going to get our answer. Negative no, it's no negative, sorry. So we don't have to worry about the negative. So 0.0575. And so again, that's the only thing to keep in mind. The r does not actually have a negative the way that we've set up the model. So we're going to do ln of 2. So let me put this out here. So ln of 2, and then we're going to divide by 0.0575. And just do this all in one fell swoop, hit enter, and the half-life is about 12.05 days. Okay, so with that being said, and it takes 12.05 days to decay from half of its original mass. So at this time, it will be, instead of 400 grams like we started with, it will become 200 grams, so half of the, which is half of the original amount that we started with. Okay? That concludes this lecture.